So here's a problem that'll use that basic strategy. We want to consider an airbag in a car. Suppose a person can survive a collision as long as they experience an acceleration that is never more than 250 meters per second squared, about 25 g. Suppose we're in a car crash starting at 65 miles per hour or 105 kilometers per hour and crashes suddenly. If the passenger is to survive, what is the minimum distance the airbag must allow them to stop in? Now this we can look at and say, all right, this seems like the category of a kinematics problem. We're just describing how quickly they come to a stop. We can make the simplifying assumption of constant acceleration. And now we can draw our non-mathematical representation, we can list some key principles, and we can use that to find what distance it needs in order to stop safely. So let's see if we can figure out what our knowns and unknowns are in this problem. We know that our acceleration is 250 meters per second squared. Now I am going to call to the right positive, and I'm going to say that my initial velocity is also to the right, which means this acceleration, in order to stop me, must be in the opposite direction. So it has to be negative. We know that our initial velocity is 105 kilometers per hour. Well, maybe we should convert that. So that's 1,000 meters per kilometer and 1 hour for every 3,600 seconds. Or in other words, (29.2) meters per second. Just a little faster than the 60 miles per hour we were using in the previous problem. The final velocity, well, that we know too. When we're done with the crash, we're going to be stopped, so the final velocity is 0. We do not know the time. It's not really what we're after. What we are after is the distance, or the displacement, delta x. Okay. So now, how are we going to deal with this? How are we going to find all this information? Let's see if I can shrink this down enough to... Yep. Group. Copy it. All right. Well, let's look at what our equations are. And let's draw out a non-mathematical representation. So I can draw, here's my velocity, here's my time. It's going to be something like that. And I want to know what this distance in here is. Now I could use what I did in the previous problem and say, hey, I can find that area in terms of the velocity and the time, but I don't know the time yet. Let's go back to our fundamental equations. We've got v equals v naught plus at, and we've got delta x equals v naught t plus 1/2 a t squared. Well, I could solve one of these equations for time and plug it into the other one. This one's a quadratic equation, generally not the best way to go solving. This one is linear, so I could solve this one for time and plug it into the other one. I could also use that other equation I mentioned. This is mathematically a little easier. So I could solve this one for time and plug it into this equation. Remember, this equation just comes from solving this one for acceleration and plugging it in here. So let's try that. If we solve this one for time, I find that the time is equal to v minus v naught divided by the acceleration. If I plug it in here, I find that delta x is equal to 1/2 v naught plus v final times v final minus v naught, all divided by the acceleration. Let's group this and make it a little smaller. Never mind. We'll move on to another spot. So this tells me that delta x is equal to 1 over 2a times v squared minus the initial velocity squared, where this is the final velocity squared. All right, now I can stick in my numbers and I can find an answer. Okay, so this is (1) divided by 2 times negative 250 meters per second squared times 0 squared, because that's my final velocity, minus 29.2 meters per second squared. Notice this negative sign will cancel with this negative sign. And when I divide, I get that I need a distance of 1.70 meters. Now you may look at that and say, well, I'm not sure that's reasonable because there aren't 1.7 meters that the airbag collapses. And in fact, if you drive at this speed into something so hard that you have no crumple room, you will probably still die. This is a very dangerous situation. But you have to remember that in addition to the airbag, you also have the crumple area in the car. And so having 1.7 meters is not that extreme. That is a possible stopping distance you might have. And as long as the seatbelt and the airbag combine to make sure you stop uniformly along with the car, you have a decent chance of surviving. The danger is when you don't have those restraints, the entire car stops, and then you slam into the dashboard and stop within a matter of a few centimeters, rather than nearly 2 meters of stopping distance.